Hello and welcome to the Problem Corner solution. This is the Problem Corner done for the September 2024 newsletter in conjunction with the International Group for Mathematical Creativity and Giftedness, or IGMCG. And you can learn more about them at the link down below in the description. Their website is igmcg.org. This newsletter I work in partnership in conjunction with Editor-in-Chief Scott Chamberlain out of the University of Wyoming and Associate Editor Christine Weiss from the University of Ohio. And it is a pleasure and a privilege to work with both of them, and I'm honored to do so. So as such, let's go ahead and get into this problem. I have not done this one yet prior to my test solve of it when I was searching for a problem to do for this section of the Problem Corner. So I really enjoyed it, and I have a favorite tactic that came up in it that I thought you might enjoy the application of as well. Let's go ahead and start reading. It's the 2023 American Mathematics Competition put out by the Math Association of America. This is the 12A, problem number 17. Flora the frog starts at 0 on the number line and makes a sequence of jumps to the right. In any one jump, independent of previous jumps, Flora leaps a positive integer distance m. So let's just make sense of this. We got some kind of number line, right? We've got 0 is where she starts. And what is the probability? Oh, hold on. Distance m with probability 1 over 2m. So for instance, if she was to jump, let's just pick something like to go to 2, the chance of her going from 0 to 2 would be 1 over 2 squared, that the m matches the integer distance jumping. What is the probability that Flora will eventually land at 10? Now we don't care what happens after 10. None of that is among our interests. We just want to know the chance that she eventually lands there. So how do we approach this? And that's kind of the start of it. Like, well, what could I do? And so I typically tell my students that if you don't know how to start, a great place to start is casework. Just throw some examples at it. Little baby steps, see what you can come up with. Let's say maybe if I was going to make cases, what might it be? Well, there's nothing saying that Flora cannot jump from 0 to 10 in one jump. It would just be the chance of that happening is 1 over 2 to the 10th. So let's call that case 1. We'll start off with you're going one jump. It's 0 to 10, one shot. The chance of that happening is 1 over 2 to the 10th. And so we say, okay, we're satisfied with that. Let's go ahead and look at case 2. Case 2 we could say is 2 jumps. We're going to do it in 2 jumps. What might that look like? And you think, well, it would have to add up to 10. So like 1 and 9, 2 and 8. Let's write some of these out. So we'll have 1 9, I guess, and then 2 8, and then 3 7, and 4 6, all the way to, you're going to end up at 9 1. And so you say, all right, let's take just one of those and figure out its probability. Since each of these 2 jumps would be independent, we are allowed to multiply their probabilities. The chance that Flora would go from 0 to 1 is a 1 in 2 chance. So I would simply multiply 1 over 2 times, that was an arrow originally, and then it became a slash when I changed my mind on the notation. So 1 over 2 times the chance that she's going to go 9 jumps on the next one, 9 integers, is 1 over 2 to the 9th. We say, okay, now we're going to have to add because all of these fall under case 2 involving 2 jumps. The chance that Flora will go from 0 to 2, of course, would just be 1 over 2 squared. So we say 1 over 2 squared, and we have times, again, the next 8 jumps all at once would be 1 over 2 to the 8th. And so we look at this and we look for a little bit of pattern. There's something here that we could capitalize on, and we start to notice, hey, 2 to the 1st times 2 to the 9th, that's 2 to the 10th, and 2 squared times 2 to the 8th, that's 2 to the 10th, and we had another 2 to the 10th up here. I wonder if they're all going to come out to 2 to the 10th. And so you kind of have these little thoughts that kind of, it's like, a hypothesis perhaps. You want to try to establish its truth. Let's pick something random like 2, 3, 5 in a case 3 situation where there's going to be 3 jumps. This would be a 1 over 2 squared times the chance she goes forward to the 5th mark on here, which is from 2 to 5. Of course, a jump of 3 will be 1 over 2 to the third. And then, of course, jumping all the way to the 10th one on that next jump would be 1 over 2 to the 5th. The denominator, again, the familiar 1 over 2 to the 10th. So now it just seems, well, rather than try to do this, this reminds me of maybe we're just trying to take the number 10 and break it up into how many partitions we can create. And partitions is a subject that comes up in one of the intermediate texts from the Art of Problem Solving. And we might explore it for a moment. We might think, let's just kind of revisit in our thoughts. At the time when I was solving it, I was like, do I even remember the partitions formula? And I don't really remember it, so I thought maybe I would just generate it, right? Let's just try to come up with it on our own. So I explored a few things. If you take the number 2 and you were to break it up into, either you could have 2 or you could have 1 and 1. And so you would get 2 ways here. And then you say, well, what about the number 3? I could have 3 by itself, I could have 1 with 2, or I could have 1, 1, and 1. And you get 3 ways, right? 3 ways. So you say, okay, but I can actually do arrangements for 3. The partitions formula, if I remember correctly, I don't think it does different orders of the 1, 2, like say a 2, 1 situation. So even if I could generate the formula for it, I pretty much remember that it doesn't necessarily do a different ordering or a permutation of the numbers. So at that point it became, well, should I really continue to pursue my dream of proving partitions right here on the spot, the formula for it? Or perhaps there's something else we could do. Because you wouldn't rearrange these, and what would I do if I got to like a 2, 2, 8 situation? There'd be so many different things that have, some duplicates and then 3 duplicates and things like that, that you'd have 3 1s and a 7, etc. It gets a little bit more, what if there's 2 2s and 2 4s? And I don't know that partitions is going to be the way to go then at that point. So we go back to the drawing board and we think, well, case 1 had one way. Isn't case 2 just essentially like I put 1 here and 9 here, 2 here and 8 here? There's, of course, 9 ways. All of these numerators will be 1, and I've got 9 of those. So maybe I could just say it's something over 2 to the 10th, and I've got 1 plus 9 plus. Now I'd be looking for what? I'd be looking to make how many of the case 3 we thought about, right? The case 3 being something like, 2, 3, 5 scenario. How many of those could I create? It's almost like I'm taking a bunch of marbles, say like 10 of them, 4, 5, 6, 7, 8, 9, 10. And I would like to place dividers between these marbles to break them up into groups. One might even call them stars, and that might give you a clue as to what a favorite tactic we are about to use. Say, for instance, this 2, 3, 5, I can go 2, 3, 5, 2 on the first jump, 3 on the second, 5 on the third. But isn't this basically then, since these are all like identical, isn't it basically how many ways could I divide 10 marbles into 3 groups? Isn't that essentially what we call stars and bars? Stars and bars is a very famous concept in the competitions, and it's a lot of fun to try to apply. And you don't really realize that you're going to be applying it at this point. It has other names too. Some people call it sticks and stones. Obviously this looks like more like stones and sticks here, but it's still called stars and bars as a popularly named title for it. Oftentimes we make a star and this is the bar coming down. So wait a minute, then this would be like I'm putting all 10 of them, all 10 marbles into one group. Now I'm putting 10 marbles into 2 groups. And the way that sticks and stones works, or stars and bars, is I think of it, there's a formula, but we really shouldn't be using the formula. Just think of the concept. There's going to be a place to put these dividers. Now, could I ever have 2 dividers in one spot, for instance? If that was the case, we would not use this particular version of stars and bars, but that would mean you did not jump. It just went straight up and back down again, which doesn't really happen because floor is going to be going forward each time. And to the right. So make a sequence of jumps to the right and a positive integer distance m with probability 1 over 2 to the m. So it has to be a positive integer distance. You can't jump 0. So at that point, there's no way that you can have a double bar. And again, if you did, you would not use this particular version. But now we can just count the gaps. There's 9 gaps between our stones. And I'd like to place 2 dividers in the gaps. So then this would have been 9 gaps, choose 0 dividers. And the next one would have been 9 gaps, choose 1 divider. And that fits with our 1 plus our 9. And at this point, most of the trained students are just off to the races and essentially done. You're just going to be able to follow the path from that point. You've got 9, choose 2 dividers. The 2 dividers creates 3 groups. You'll continue this process all the way to the chance that Flora jumps 1 every single time, essentially putting a divider between each and every star or each and every stone. That would be all the way to 9, choose 9. And of course, the summation of this is going to be 2 to the 9th power. So when you put 2 to the 9th over 2 to the 10th, you're going to end up with 1/2. So I really like this because you kind of don't see stars and bars coming. You don't see it coming on the path. It kind of doesn't, you're just coming around a corner all of a sudden. You're like, wait a minute, we're just breaking the number 10 up, but isn't the number 10 like just like a bunch of stones, kind of like values of 1, and we're putting them into like 3 piles and then 4 piles, and then that's exactly what stars and bars is. And so once you see it, it kind of just falls apart at that point. There is about, I think, 12 different solutions showing on the AOPS forums for this problem. Maybe you might have found a different one than this, but I sure hope you enjoyed this solution. I will see you in the next edition of the March newsletter come next year. You have a good one.